Great. Now that we've figured out all that we need to know about bonding, we're going to go and focus on our different states of matter. So we'll start with gases. You can see the sequence of what we'll go through here. We'll talk a little bit about the characteristics of gases, define some pressure units that we'll use for gases, and then we'll get right into the gas laws. Most of the gas laws we're going to do as a classroom activity. Then we'll also do some work with the ideal gas law, obviously involving quite a bit of math, applications of the gas laws, mixtures, partial pressures, the kinetic molecular theory, so we'll be looking at explaining why all these laws operate the way they do, and then talk a little bit about effusion, diffusion, and real versus ideal gases. All right, so let's start out with some characteristics of gases. So I'll just go through a list of things. First of all, gas particles are pretty far apart from each other relative to solids and liquids. Gases will take on the volume and the shape of the container. Given that the particles are actually very far apart, the volume of the particle itself is actually going to be rather insignificant compared to the volume that the gas takes up overall. Similar, to this is that, because those particles are so far apart, we can easily compress gases. Gases do flow, and we'll do a couple demonstrations in class with this, and perhaps some of you will do this for your mole day presentations. Gases have higher energy than both liquids or solids. We assume that gas particles have little or no attractive or repulsive forces for each other. This is where we're going to get into some problems at the end of the chapter when we look at real gases. And finally, in terms of the energy part here, we know that the energy of gases, the motion of them is the kinetic energy, which is 1/2 mv squared. We learned from one of the other chapters where we're studying the energy of particles, and we know that the kinetic energy is proportional to the Kelvin temperature. Over on the right here we have the kinetic energy distribution curve, and we'll go over some examples of that in class and have each group kind of work with that at different, find out different temperatures and analyze and interpreting that graph. Here we have common compounds that are gases at room temperatures. Some things that we run into on a daily basis: carbon dioxide, colorless and odorless. Basically, we breathe it out all the time, not very harmful to us. Methane, otherwise known as natural gas, used for a lot of home heating and hot water heaters for stoves and things like that. It's colorless, normally odorless, although the methane that we use for natural gas has a substance in it that makes it smell, so that if there's a leak we'd be able to tell. Propane, colorless, bottled gas. That's what we use for our barbecues at the summertime. And let's see, carbon monoxide, toxic and colorless and odorless. Again, this is one that it's oftentimes given off from a car. The carbon monoxide binds to hemoglobin molecules similar to the way iron does, and it prevents oxygen from getting through your system. We need to address the measuring of pressure and pressure units. So one of the things we don't really have a good feeling for is how much pressure is around us all the time due to the gases that are surrounding us. And where does that pressure come from? Well, if we think about diving down into a pool, if you go down deep into a pool, now you can feel the pressure of the water that's on top of you pushing on your eardrums. air is basically like a sea, or the atmosphere is basically like a sea of air. So all that air that's piled on top of you actually does create the pressure that we feel, or that we would feel. And there's miles of air pushing down on top of us. So although air isn't as dense as water, that cumulative effect actually creates quite a bit of pressure pushing down on us. From a physics standpoint, we have pressure is equal to force over area. So the pressure that's exerted by some object is equal to the force that it's being pushed, the force that it's pushing divided by the area that force is spread out over. So we get a few different units then from this. First of all is the practical unit, which comes about from the fact that when they started doing experiments with gases, they would use liquid mercury to measure the difference in pressure of a gas compared to the atmosphere. So you can see in the picture here, you've got a eudiometer tube in which there's gas over in the container on the left, and it's open up to the air on the right. And you see that the difference between the mercury inside the tube and outside the tube is given by H there. This tells you that the pressure of the gas is H millimeters of mercury greater than the pressure of the atmosphere outside. So millimeters of mercury and millimeters being the height, ended up being a very practical unit for pressure. If we go to our physics, our derived unit, we have pressure is equal to force divided by area. And so our standard unit of force is a Newton. So if we exert a force of 1 Newton over an area of 1 square meter, our standard unit of meter, we get what is called a Pascal. Okay. Now you can imagine one Newton of force isn't very great. It would be less than the force of an apple in your hand. Perhaps a golf ball in your hand would exert 1 Newton of force down on your hand. So if you spread that over a square meter, that's not very much. So most of the time we're going to deal in units of kilopascals, or kPa. All right, next we have our common sense unit. So this would be similar like in the temperature scale where you have the Celsius scale where 0 degrees Celsius is the freezing point of water, 100 degrees Celsius is the boiling point of water. From a common sense standpoint, we would want to make, we want to come up with a standard pressure that made sense. And the one that we would use is the pressure at sea level. The pressure at sea level. And the units, or the scale that has a pressure that uses pressure of sea level as a standard, are called atmospheres. And so the pressure at sea level is equal to 1.00 atmospheres. Now, to convert back and forth between each of these things, which we'll have to do in several of our problems, 1.00 atmospheres is equal to 101.3 kilopascals and 760 millimeters of mercury. Now, you may also see millimeters of mercury listed as torr. And so that was another unit that was used. It meant the same thing, millimeters of mercury, but it was just given a different name. Here we have a barometer that was used to measure atmospheric pressure. And basically what they would do is they would take a long glass tube and they would fill it up with mercury, take that tube, tip it over so that none of the mercury was allowed to get out, and then invert it into a pool of mercury. Now, you've probably done this with a bottle of water or something at some point, where you fill the bottle up with water and you start to pull out of the water, and if you have it submerged below the water, if you try to pull it up out of the water that's inside the bottle, if it's upside down, stays inside the bottle. The reason for this is that you have the atmosphere pushing on the surface of the liquid. So literally that atmospheric pressure that's on the surface of the liquid here is actually pushing and holding the mercury up inside that tube. Now mercury, because it's so dense, that pressure can only push so hard, so you create a vacuum up at the top of the tube. Right? Now, if the pressure outside is rather high, then you get more pressure pushing on there, and the level of the mercury goes up. If the pressure outside is low, we're in a low pressure day, then there would be less pressure on the surface of the pool of mercury, and the column of mercury inside the tube would go down. So this height then could be used to measure the pressure, the air pressure outside. If you're studying a gas, then over here on the right, you could look at, once you determine the pressure of the atmosphere, you could use that to compare or to measure the pressure of the gas that's inside a container. So in the picture up here, obviously the pressure of the air is pushing down less hard with less pressure than the gas. You can see the two levels here, right, where the pressure of the gas is that the difference in the height there. That's the difference between the pressure of the gas and the pressure of the air. All right. So now that we've looked at pressure, and we're all pretty familiar with measuring temperature, we're going to want to get into the different quantitative characteristics of gases and the variables that we should remember from our studies before. We have the pressure we just talked about, volume, which we should be pretty adept at measuring, temperature, and N being the number of moles of particles. So what we'll do is in class we'll work on ironing out the different laws and seeing examples of these.